Good afternoon and welcome to our 2021 Solar District Cup competition presentation. We are at Triton College from Chicago, Illinois. Our process involved designing a PV system comparatively against multiple designs and financial options, substantiated by developmental software programs, NREL weather data, and budget realities. Some of the factors that influenced our decisions challenged our hypothesis and ultimately strengthened our conclusion. We also wanted to take a moment and give thanks to our team members as well as our staff. The conceptual portion of the project was led by myself, Yureli Hernandez, and my partner, Abram Galvin. The financials were conducted by Marissa Wind, while the distribution and battery storage were completed by Umi Torre and Tyler O'Connor. The participants in charge of developmental were Matthew Ellis and Trevor Cole. Lastly, a huge thank you to our captain, Professor Andrea Blaylock, and to our IBEW instructors, Robert Hadier and Joseph Kilcoyne.
So the University of Nebraska at Lincoln was established in 1869, just 2 years after Nebraska gained its statehood. The Morrill Land Grant of 1862 opened up the Western states to establish colleges of their own for specializations in agriculture and mechanics. This provided educational opportunities for those of lower classes. Like many others of its kind, it relied heavily on federal funding for this change. The campus today has its very own LEED certification, otherwise known as the Leadership in Energy and Environmental Design. Things like local and sustainable meals, transportation that runs on soy biodiesel, and buildings meeting energy efficient demands have been rewarded with a LEED silver rating as well as tax incentives. This is a clear example of how green energy produces financial benefits. Next slide.
I think it's on the campus.
The NREL slide. Yeah. Given the location of the campus and the NREL data collected, we used 5.08 peak sun hours as shown, or the daily nominal radiance here. This shows us for an average of 5 hours a day, these solar panels will produce electricity. The average DNI being about 4.5 shows us that we are expected to receive above average levels of sun.
So why solar? We want to steer away from traditional power plant generation, which produces 1.9 billion tons of CO2. And we can talk about figures and finances, but we want to give a quick background on why solar is so incredible and beneficial. We recognize the awesome process that is solar energy, and not to take for granted electricity production from the sun. The sun produces 23,000 terawatt hours annually. Well, on Earth, we only use about 16 terawatts a year, which means the sun releases enough energy in 1 hour to power the entire Earth for an entire year. It's also little thought of that all forms of renewable energy actually come from the sun. Wind power is created by warm and cold fronts moving on Earth, created by the sun. Hydropower originates from the sun using the hydrologic cycle. The sun is even responsible for fossil fuels. If you think about trees and plants that become coal, are here because of the sun. And we just want to cut the middleman out of the equation. And we're finally at a time with renewable energy technology, such as solar, that it can finally be financially competitive with the carbon-based fossil fuel industry.
So initially, the concept was to size the system for maximum space. The first design led us to a 5.5 megawatt system, which turned out to be 3 times the amount of electricity the university would need in a month. Based on the lack of net metering incentives and Nebraska's net metering law, it was clearly overproducing was not going to be beneficial for us. After considering the total amount of batteries that would be needed to store such a large amount of the excessive price add-on, we decided to drastically lower our system to about 2.5 megawatts to create a more sustainable and financially realistic system.
So on campus, there's about 800,000 square feet of usable rooftop space, 200,000 of those 800,000 square feet belonging to the Animal Science Building alone. And there is also 300,000 square feet of parking lot space.
As previously mentioned, the East Campus has about 300,000 square feet of parking space. We wanted to utilize the space with the addition of carports. This is done in an effort to maximize our potential output reimagine design possibilities, and as well as serve as a hub for potential EV charging stations, which award LEED building credits, the system that the college is currently striving for. And a fact that is little talked about, it creates solar awareness. If we only used rooftop space, no one could see our design system. And the externalities of visible solar are massive. By using carports, we wanted to create a conversation about solar power and to put energy transition into the college mindset and to ultimately get people excited about it.
So as mentioned before, our system size was 2.5 megawatts. Combined with the peak sun hours of around 5, the average production per day would be about 12.7 megawatts. Per month, that puts us just under 400 megawatts, and per year, just under 5,000 megawatts. The system percentage rooftop that we wanted to install was about 70%, and the other 30% being carports. The system is designed to cover maximum energy demands during higher demanding summer months while exporting excess energy to potential carport EV stations via our smart grid.
So we decided to go with the SunPower Performance Series P17. It's a 355 watt panel, which is currently one of the highest producing panels on the market. It is top of the line. Rated voltage at about 43.4 and 8.18 amps. It's optimized for larger projects like our college system. The warranty is what really stands out for this panel. Most panels are only warranted for about 10 years, and these will last for the entire time of our project projections. The power of the panel is also warranted for much higher production. At the end of 25 years, it'll still be rated for 82.6% of its production.
So inverters are, of course, essential to any solar project as they convert DC power into usable AC. The particular three-phase inverter we chose has an output of 20,000 volts and has smart inverter capabilities. These smart technologies include wireless connection to the inverters for maximum performance returns. The computer programming accompanied by these inverters themselves allows for GPS mapping to pinpoint problem areas in the system. Most importantly, these machines are designed specifically to work with power optimizers. We decided on tying each building system together by connecting all of the inverters, making the University of Nebraska at Lincoln its own smart grid. That very same grid will have the capability to send overproduction to buildings in need by way of those inverters. This will ensure that all energies produced by the system are utilized efficiently.
So for our power optimizers, we went with the SolarEdge P400. It is a 400 watt optimizer. These power optimizers have up to 25% more energy, and they have a efficiency rating of 99.5%.
So the project's construction work would need to be subcontracted. The related personnel will
So pause the clock, please. So for the Triton College team members, it looks like the internet connection for Trevor Cole has been interrupted. We can wait a few seconds, or one of you could.
Sorry.
So,
I think I cut out
Trevor,
a little
your
bit
internet.
on that slide.
Yep, Trevor, your internet connection stalled out. So would you be sure to minimize anything else you have going on in the background of your computer so that the Zoom meeting can have the most bandwidth?
Yes.
We lost you just as you started on this developmental plan slide. So Logan, would you restart the clock? Trevor, please continue.
Sure. So the project's construction work would need to be subcontracted. The related personnel would include laborers, craftsmen, supervisors, supply personnel, and construction managers. The project will need to ensure that the following services are provided. So environmental health safety training, site first aid, site fire protection, trash collection and disposal, and disposal of hazardous materials and waste in accordance with local, state, and federal regulations. Nebraska follows the NFPA 70 NEC, and that's the 2017 code book, although not much has changed for their state of Nebraska with respect to the Article 690, including these photovoltaics. A mandatory space of 3 feet between arrays and the edge of the buildings, as well as the walkways that will be constructed in compliance with the Nebraska statewide fire protection codes.
So the entire East Campus uses an average of 6,637 kilowatts per day. That is a monthly usage of about 205 megawatt hours. That's an annual usage of 2.4 gigawatt hours. And as you can see here, the campus uses more than 100,000 kilowatt hours per month, so it falls into the rate 1516 of large light and power. These energy companies' scale prices makes it incredibly cheap for these large demand industries such as college campuses, which unfortunately make an energy transition financially difficult. The large light and power rate charges more for the summer months at 2.6 cents, while the winter and spring months are rated at 2.3 cents. And this graph here shows how the campus uses more during those higher summer months.
So most buildings on the campus grounds produce most of the energy before peak energy hours, meaning 9 a.m. to 6 p.m. In contrast to Nebraska's peak energy hours, which are 3 p.m. to 8 p.m. There are 2 buildings on campus that produce the most energy by far, those being the Animal Sciences building coming in at 500 kilowatts and the Food Industry building at 150 kilowatts. In configuring a battery storage situation, we looked at the Tesla Powerwall models that have a capacity of about 13 kilowatts per unit. To power both of those buildings alone would be about $400,000 to reach the demand of these 2 facilities, not to mention the amount of storage needs to house these power units.
So we ran the OpenDSS to monitor our power distribution. Using the source code, we set the PV line and PV transformer and set the temperature and radiance data. We ran the software monitoring voltages and power flow, ended up creating a safe and sound distribution system. No faults or over voltages were found within our margins. The distribution analysis showed our system can be safely transported to the grid without avoiding any voltage violations and thermal overloading, while maintaining power quality. As another safety measure, with the advantages of our smart inverters, we can transport energy where it is needed most on campus, as well as clip any excess production over 2 megawatts. Although our calculations showed no risk of interconnection to the grid, it is Nebraska state mandated for the local utility to run an independent study.
So for our financial options, we first looked at a cash payment plan. The return on investment of that plan was about 30 years. Equally important was the internal rate of return, which is about 7.75%, with an upfront cost of about $4 million. The second plan that we looked at was a loan payment option. So 50% of that, so 2.4 million, would be put up front. The interest rate for that would be 6.99%. With expected low tax return rate for an investor early on. And finally, a PPA was our last option with no upfront costs. And we actually spoke to GRNE, a solar company in Lincoln, Nebraska, about the rate of 4 cents per kilowatt or $40 per megawatt. The average bill would be about $98,000. The total cost of the system would be $2.9 million over 30 years.
So there are 2 incentives through the local utility LES that offers a one-time rebate of south or west-facing panels, which we do qualify for. We have designed the proposal for rooftop space, and we did not design it for any of the pitch roofs. So Nebraska also offers a tax exemption on renewable energy-related products. Unfortunately, there are not many other state incentives such as SRECs in Nebraska. Federal incentives do help create change, just like the Moral Land Grant, which helped establish the University of Nebraska, we would love to have more support for energy needs on our campuses. Education as well as transitioning to a new energy future are both important federal investments. Doing so established as a cleaner college campus, providing an example for nationwide colleges and thus a cleaner nation.
Ultimately, we chose the PPA leasing agreement. We did that because you never start with a negative cash flow or a negative return. Although the cash flow is very minimal, it consistently increases as your plan continues. The PPA allows for no debt or interest to accumulate, which in turn makes the system more profitable for the university. Also, as stated previously, the PPA financial plan will give you a projected IRR of 7.55%.
So thank you for joining us and for taking the time to listen to our presentation. We recognize that although this is a conceptual competition, we do truly believe in the philosophy of green energy and hope the University of Nebraska implements a large-scale solar design. We will now be open to any questions.